Hi everybody, here's a video going over homework 8 as requested. One of the things that makes this proof a little more difficult to see is that it involves two overlapping triangles. There's one of them, and there's the other. So it might actually be helpful to draw them as two separate triangles before you get started. So that is triangle GAT, and that is triangle ETA. One interesting thing about these two triangles is that they share a segment AT. We're not used to seeing the reflexive property in a way that looks like this, but AT is actually a reflexive segment. So we'll get to that in a minute. First off, the first given, it looks like it's going to be a nice quick one because it gives me two segments that are congruent to each other. Let me just make sure that they're actually in the triangle. GA, ET, tick, tick. So that's my first pair of congruent segments. So no follow-up step needed, which is kind of nice. Step 2 is also a pair of congruent segments. Let's see if these ones are in the triangles or not. These ones are, but they're a little harder to label because it's GT and EA. Sometimes I'll put little brackets with tick marks, but it is a little easier to see on my separate triangles. So that's another pair of congruent segments. So we're out of givens. We need a third thing. I already mentioned to you that AT is congruent to itself by the reflexive property. So that is going to be step 3. And it's looking at first glance like this is going to be a pretty quick proof because we already have 3 things. So we're already ready for our congruent triangles. So the way that I can name them, it's easier when I look at my separated triangles. Triangle GAT is congruent to triangle ETA. And that is by side, side, side. I wasn't given any angles, and there's no vertical angles in these overlapping triangles. There's vertical angles in the picture, but they're not really that helpful in the overlapping triangles. Okay, here is where this gets complicated. I'm going to erase all of my highlighting and even my separated triangles and take a look at what I'm trying to prove. So this is what makes this proof a little bit more difficult. I'm trying to get that these little segments are congruent. Those little segments are not part of my congruent triangles, but they are segments in a little mini isosceles triangle that's here in the middle. So I don't really have a way to go directly to those segments, but I do have a way of getting to those angles. And what we've learned about isosceles triangles is if it's isosceles, it has congruent legs and it has congruent base angles. So those little angles actually are angles that are in the triangles that we just proved congruent. So those little angles I can say are congruent by CPCTC. So I'm going to call them angle EAT and angle GTA by CPCTC. So I needed to do that first, then I can draw my conclusion and say, well, now I know that the triangle is isosceles, so now I do know that those little segments are congruent to each other. We can say this in words, or we can actually even just do it in a picture. We can say if the little base angles are congruent, then the legs are congruent. So that's a step that we haven't actually used in any of our proofs yet. So that one not too long, but a little tricky with the problem solving that got to proving the conclusion. All right, number 2 I think might be a little bit longer because this one needs a bunch of follow-up steps. So it came up in class that if you're given to have a circle, it's almost always so that you can use radii in the circle that are congruent to each other. So that's going to be the follow-up step. We need that AM and ME are congruent because it's a circle, so the radii are congruent. So that's my first pair of congruent things. So I'm going to highlight those. Now I can move on to the next given. AE is perpendicular to CM. Once again, I need a follow-up step because that doesn't actually give me that anything's congruent. But when I mark the right angles, because that's what I do with perpendicular lines, now I have some congruent right angles. So M has to be the middle letter. I'm going to call them angle FME and angle FMA. And my reason, if I use my vocab, has to have something to do with perpendicular lines. So I'm going to say perpendicular lines give us congruent right angles. So now I have 2 things. I need a third. I have another given, but I'm actually not going to use it right now. I'm going to use this reflexive segment instead because I think that given might be for something else that we need later. So I'm going to say FM is congruent to itself by the reflexive property. And now we have our 3 congruent things. So now we're ready to say that the triangles are congruent to each other. So I'm going to call them FMA and FME. And the markings that I have are side, angle, side. So now we're on to the part where we need to figure out what we're going to steal by CPCTC. So it asks me to prove that AD and BE are congruent. Those segments are too big. They're not actually part of my congruent triangles. So I'm going to steal the smaller segments that actually are part of the congruent triangles. And that's what I'm going to use CPCTC for. So I'm going to say AF is congruent to FE by CPCTC. And then if you're wondering how that helps, now that other extra given comes in, I actually gave you that these little segments on the top, BF and FD, are congruent to each other also. So we can put those together to make the big segments. So I'm going to say BF and DF are congruent because that was given. And now I can add together AF and FD to make AD, and I can add together FE and BF to make BE. So I'm ready to draw my final conclusion. So I'm going to copy paste the step that I'm trying to prove. And that's another step that we haven't actually done in class yet, but I'm taking congruent segments and adding them to congruent segments. So it's called the addition property. Let me know if you have any questions. Thanks for watching.